All right, so now we're going to talk about pointers. Some of you may have had experience with pointers before, some of you may not have. That's okay. I'm going to go through the pointer mechanics first, and then we're going to start looking at how memory works in Go. Again, we're moving towards talking about integrity and readability, constantly. If you're starting here, please, I want you to start from the beginning. It's really important. It's going to lead up to everything that I'm about to talk to you about. Now, the one thing we have to understand about Go is everything is about pass by value. And pass by value for me is WYSIWYG. What you see is what you get. And you get integrity and readability through pass by value. So we're going to see that now by just looking at some pointer mechanics to understand things. Now there's another thing you have to understand about pointers. Pointers value across a program boundary. There are several different types of program boundaries. The most common one will be between function calls. But we could have a program boundary between Go routines, as we'll talk more later when we get into concurrency. For now, we're going to talk about function call program boundaries. And so for sharing a value, we need a pointer. So let's get into this. Let's go through this mechanic. Now, the next thing we have to understand is the following. When this Go program starts up, the runtime is going to create what we call a Go routine. Now, I'm not ready to go deep into Go routines yet. We'll get there. But we do need to have a basic understanding of what we're talking about. I want you to think of a Go routine as a path of execution. All the code you write executes on a Go routine. You can think of it as a thread if you want to right now, because the Go scheduler at some point does have to place that Go routine on an operating system thread so it can execute. So think of every Go routine right now as a separate path of execution that contains the instructions you're writing that need to get executed by the machine. This program has a single Go routine, the main Go routine that's going to be executed or created by the runtime and therefore executed to execute all the instructions that we see. Now in Go, every Go routine is given a block of memory that we call the stack. Now this stack memory in Go starts out as 2K. K, very, very small. This number has changed over time. It was 4K for a long time, but now today it is 2K. And to put this in perspective, every operating system thread generally is given a meg of memory. Think about it right now. Every Go routine stack is just starting out at 2K. Go is about using resources efficiently on top of everything else in terms of integrity and readability. So this block of memory, this 2K stack, has been allocated for this Go routine. And every time a function is called, a piece of this stack is used to help that function run. What we see here is function main. And at some point, the runtime will have this main Go routine execute this main function. And when it does, it will take a piece of that memory from the stack. Now, it's just an implementation detail. It means nothing, but you're going to see me work this stack in a downward direction. It is purely an implementation detail. It means absolutely nothing, but it's how things are working today. And when we start looking at addresses, you should see these addresses going lower, showing that we are working the stack down and not up. Now, what's important here is on line 10, I have a variable declared. It's called count. And what we've done here, this piece of memory that I've taken off of the stack, we're going to call a stack frame. Every function is given a stack frame to work against. I want you to think of this stack frame as memory specific for the execution of this function. Now, what's really interesting about the stack frame is that the size of every stack frame is known at compile time. Now, why is that significant? That's significant because what this means is no value can be placed on a stack unless the compiler knows the size of it ahead of time, because the size of every frame for every function has to be known at compile time. It is known before the program executes. So if we don't know the size of something at compile time, it has to be on this other piece of memory that we call the heap. If we know the size of it ahead of time, there is an opportunity for it to be on the stack. But let's keep talking about pass by value. In this particular case, we have the variable count. We know the size of count. From a playground perspective, it is 4 bytes of memory, and we've put the value of 10 in those 4 bytes of memory on the stack frame for main. Now, here on line 13, I'm using the built-in function printline to display both the value of count and its address. I want to get away a little bit from operators here for a second. Anytime you see a variable by itself, like this, like count, we see it by itself, I want you to think value of what's in the box. Here I'm saying display the value of count. What's in the box? 10. Now, Go uses this ampersand operator. It is not unique. Go is not being novel. This is an operator that C has used for a long time. And what the operator says is address of where is the box. If the box is in memory, then it must have some sort of address. In this case, a 32-bit address. I'm just using 4 characters to represent a potential address that it might be on. Addresses are in hexadecimal numbers. Okay, so I've asked to say display what's in the box, the value of count, the address of count, where is the box. And then on line 16, I make a function call. You know function calls. You've been writing functions your whole life. What I want you to do is look at the mechanics here. Look at this a little bit differently. Now, if you notice on line 16, this function call is passing a value, right? It's passing a value across this program boundary, which is going to be the value of count, which we know is an integer. Pass by value means that something is always being copied, either the value itself or its address. And in this case, we're passing the value of count itself. Now, in order to pass this value across, the other side must catch it. And to catch it, we must have a variable declared of the right type. And this is where parameters come in. You've been doing this your whole life. There's nothing novel here. What I want you to do is start connecting the dots here between that function call and the parameter you've declared. That parameter is there to catch, to store the value that we are passing across this program boundary. Now, when we make this function call, what's going to happen? We need to take a piece of that memory again off the stack for this function's frame. Now, here's increment. Again, the size of this frame is known at compile time. It could be different sizes. I've kind of drawn them equally here. That doesn't necessarily have to be the case. And this parameter is going to be a variable on this stack inside this frame. This is the inc. And since we passed the value of count, increment is going to receive that value. Its job is, its purpose is to store that value we're passing across the program boundary. Okay, brilliant. Now, when we look at the increment function operates against its values, its variables that sit inside its local frame. Technically, this is all, from our perspective here, that these functions can do. This memory is specific to this function call. This memory here is specific to this function call. It gets to operate against this. And on this plus plus, which is that read modify write, we're going to change this value from 10 to 11. And then we go ahead and display the value of count, or inc, what's in the box. And then we display its address. And if I run this code, what we're going to see at the bottom is that the count variable inside this stack frame on this GoRoutine stack is at address 9FA, or is that 9? Oh, sorry, I wrote that wrong. 9FA4, 9FA4. And if we look now at the next one, it's 9F98, 9F98. And you can see that the address is smaller, lower on the stack. And it would really help if I could write these things correctly for you here. But you know, here we go, 9F98, 9F98. There we go. And again, we see that this value is lower in memory. It's lower on the stack. It's in its own stack frame. And this is what we're seeing. Okay, great. Now, once this function returns, we come back up to main, and we display the value of and the address of count again, you can see that nothing has changed up here. Now, we call this a stack. So you might have this idea in your head that a return is like a pop, where we're going to pop this off the stack. But that is absolutely not the case. This memory is here for our use and here for reuse. Every time we call a function, again, we're going to be able to reuse this memory. The only valid memory on the stack is where we are on our current stack frame and anything above it. Remember that. Let me show you another program. All right, so let's change this up now. Let's do the sharing. Remember, what I want is this increment function to not operate on its own copy of the value. I want it to be able to manipulate the value in main stack frame. So this time we're going to need a pointer to perform that sharing. So we're back here on line 11. We've got the value of count. There it is, it's 10. We could display its value and its address. There it is on the stack frame for main. And then we go ahead and we make one change. If you notice, we're not passing the value of count anymore. We're passing the address of count. And this is still considered a pass by value, not by reference. The thing here is, I know we are sharing or passing the address across the program boundary. But an address is a value, just like the integer is a value. Pass by value is WYSIWYG. What you see is what you get. And because we're passing this address across the program boundary by value, that means we need a variable that can store an address. And this is where pointer variables come in. I want you to look at how we've changed the declaration here. Notice now that the int variable is not based on the int type. It's based on a type called *int. And this is the pointer type declares a variable whose sole purpose is to store that address value. So pointers are for sharing, and we do that sharing by passing by value this address across the program boundary, and it is the pointer variable's job to store that address.